Repeatered submarine fiber cable. A repeatered submarine fiber cable is a long-distance optical system that uses inline optical amplifiers to keep light signals strong across an ocean. The cable contains multiple glass fibers for data, a central copper conductor for electrical power, steel strength members for tension, and outer polymer jackets for seawater protection. Along the wet plant, sealed amplifier housings called repeaters are spliced in series at regular intervals. Each repeater contains erbium-doped fiber amplifiers that boost all wavelengths passing through without converting light back to electricity. This all-optical amplification keeps noise low and preserves signal quality over thousands of kilometers. Repeaters require continuous electrical power supplied from the cable landing stations. Direct current is injected onto the copper conductor, and the seawater provides the return path, so every repeater in the chain is powered in series. Power feed equipment at the landing stations regulates voltage and current and monitors the health of the wet plant. Because the repeaters are pressure-resistant and sealed for decades, all maintenance access happens from ships that recover cable sections at sea when faults are detected. Capacity in repeatered systems comes from stacking many colors of light in each fiber using dense wavelength division multiplexing. Modern line terminal equipment in the landing stations generates and receives these wavelengths, applies coherent modulation formats, and performs digital signal processing to counteract dispersion and nonlinear effects accumulated along the span. The wet plant is designed to be as transparent as possible, so that upgrades to the terminal equipment on shore can increase capacity over the system's lifetime without touching the ocean segment. Route engineering for repeatered cables balances optical reach, seabed risk, and repair logistics. Marine surveys select paths that avoid steep slopes, submarine landslides, and high trawling intensity. In deep water, the cable typically lies directly on the seabed. In shallower zones, it is buried where feasible to reduce external aggression from anchors and fishing gear. The spacing of repeaters, the optical fiber type, and the amplifier gain plan are jointly optimized so the signal-to-noise ratio stays within the margins required by the chosen modulation and error correction. Unrepeatered submarine fiber cable. An unrepeatered submarine fiber cable is used for shorter spans where optical amplification in the seabed is not required. Instead of inline repeaters, the signal travels the entire route, with only the optical power launched from the terminal equipment on land. These systems rely on ultra-low-loss fiber, optimized transceivers, and high-powered optical amplifiers located in the cable landing stations. The distance achievable is limited by how far light can propagate before signal-to-noise degradation makes error correction ineffective. Unrepeatered systems are often deployed for regional links, festoon networks that follow coastlines, or connections between nearby islands. Typical reach is on the order of 100 to 300 kilometers, although with advanced fiber and powerful transponders, spans exceeding 400 kilometers are possible. Beyond that range, attenuation and nonlinear effects make repeaters unavoidable. Because there are no repeaters in the wet plant, unrepeatered cables are mechanically simpler and cheaper to manufacture, deploy, and maintain. They consist of the optical fiber core, protective steel armoring if required, and insulating layers, but no powered electronic housings. The absence of active components also increases long-term reliability, since only the shore-based terminal equipment requires upgrades or replacement. However, capacity is more limited than in repeatered trunk systems because launch power and amplifier noise at the terminals impose stricter limits on how many wavelengths can be transmitted simultaneously. Unrepeatered cables are particularly common in festoon topologies, where multiple landing points connect a string of coastal cities or islands. The shorter spans between landings allow operators to balance cost and coverage without the complexity of subsea repeaters. Protection and construction classes by depth. Cable construction changes with depth and seabed risk to balance protection and weight. In deep water with low external risk, the goal is low weight and low attenuation. In shallow or rough zones, the goal is abrasion resistance and crush strength. Installation plans combine burial where possible with the right armor class where burial is not feasible. Lightweight construction. Lightweight construction, often labeled LW, is used in abyssal plains and other deep areas with minimal fishing and anchoring. The design has a polymer jacket over the steel strength members with no external armor wires. It offers the lowest diameter, the lowest weight per kilometer, and the lowest optical attenuation because there is less steel and fewer mechanical interfaces. It is laid directly on the seabed. Lightweight protected construction. Lightweight protected, often labeled LWP, adds a thin protective wrap, or serving over the core to improve abrasion resistance without the mass of full armor. It is used where occasional contact with soft sediments or low levels of trawling are possible, or where the route crosses gentle slopes that could cause minor scuffing during lay. Single armored construction. Single armored, often labeled SA, adds one layer of galvanized steel wires helically wound around the core. The armor raises tensile strength for near-shore lays and provides resistance to abrasion and bites from fishing gear. It is selected for continental shelf areas, canyon edges, and routes with moderate trawling intensity. Where burial cannot be guaranteed due to hard ground, single armor provides a primary mechanical defense. Double armored construction. Double armored, often labeled DA, uses two counter-wound layers of steel armor wires for high crush resistance and ruggedness. It is deployed in very shallow waters, in zones with heavy trawling, and on steep or rocky slopes. The larger diameter spreads load when the cable spans small gaps across boulders or rough seabed, reducing point pressure and jacket damage. Heavy or rock-armored construction. Heavy armored, also called rock-armored and sometimes labeled HDA or RA, is a very dense build with large diameter wires for extreme protection. It is chosen for shore approaches with surf, cobble, or reef zones, and for sections that cannot be buried in hard rock. The goal is to survive abrasion from wave-driven movement and repetitive external impacts over decades. Shore end with articulated pipe. Very near the beach, the cable transitions into articulated iron or ductile steel pipe segments. These hinged half-shells lock around the cable to form a continuous protective conduit from just offshore up to the beach manhole. The pipe prevents damage from surf action, boat propellers, anchors, and recreational activity. The length of articulated pipe is set by local bathymetry and wave climate so that the cable is protected until it reaches buried duct or conduit on land. Fiber types in modern systems. ITUTG 654.E. This is ultra-low-loss, single-mode fiber designed for very long ocean spans. It has a larger effective area of the glass core, which spreads optical power across a wider mode field. Spreading the power lowers nonlinear effects, such as self-phase modulation and cross-phase modulation when launch power is high. Typical attenuation in the 1550 nanometer window is around 0.17 decibels per kilometer or better, which allows longer repeater spacing or higher margin. The trade-off is lower macrobend tolerance and a slightly larger preferred cable diameter to protect the glass. It is used for transoceanic trunks that push high capacity over extreme distances with coherent modulation. ITUTG 652.D. This is the mainstream standard single-mode fiber. It keeps low attenuation in the 1310 and 1550 nanometer bands and removes the water peak so that all wavelengths between are usable. It has smaller effective area than G654.E, but it tolerates tighter bends and tighter coiling, which helps in shore ends, branching units, and compact cable constructions. It is commonly chosen for regional links and festoon systems where spans are shorter and installation environments are more constrained. Modern coherent terminals can still deliver very high capacity over this fiber when distances are moderate. Legacy G655 non-zero dispersion shifted fiber. This older family shifts the dispersion so that at 1550 nanometers, the fiber has a small positive dispersion instead of near zero. The positive dispersion suppresses four-wave mixing among densely spaced wavelengths, which was critical for early dense wavelength division multiplexing systems. However, dispersion slope and compatibility issues across vendors limited upgrade paths, and coherent detection with digital signal processing reduced the need for this fiber type. Many older wet plants still operate with G655, but new builds favor G654.E for long-haul and G652.D for regional and festoon applications. Optical spectrum configurations. C-band only systems. Many modern wet plants operate only in the conventional optical band around 1,530 to 1,565 nanometers. Using a single band simplifies repeater design because each repeater carries one erbium-doped fiber amplifier chain with a single gain-flattening filter. A single band also reduces insertion loss at branching units and joints. The trade-off is a smaller usable spectrum per fiber pair, so total capacity depends more heavily on spectral efficiency of the transponders. C plus L band systems. Some long-haul systems add the long band, roughly 1,565 to 1,625 nanometers, in parallel with the C band. Each repeater then contains two independent amplifier chains, one for each band, with separate pump lasers, isolators, and gain flattening. Doubling the bands increases available spectrum per fiber pair, but raises repeater power draw and lengthens the repeater housing. System design must also manage interband isolation and equalize end-to-end gain so that both bands achieve similar signal-to-noise ratio and error correction margin. Pairing model and space division multiplexing. Non-space division multiplexed model. In the traditional model, a cable has a small number of fiber pairs. Each pair is driven hard for maximum capacity using higher launch power and high spectral efficiency formats. Repeaters allocate more pump power per amplifier, which pushes nonlinear effects closer to their limits. This design extracts the most bits per fiber pair, but is constrained by the total high voltage power that can be delivered to the wet plant over an ocean length. Space division multiplexed model. In the space division multiplexed approach, a cable carries many fiber pairs, such as 8, 12, 16, or even 24 or more. Each pair runs at lower optical power and moderate spectral efficiency, which reduces nonlinear penalties and improves energy per bit. Repeaters divide their pump power across more amplifier modules, keeping per pair noise figure low without stressing nonlinearity limits. The outcome is higher total cable capacity within the same end-to-end power feed budget. The trade-off is more fibers, more amplifier modules per repeater, larger branching units, and more transponder ports on shore. Power feed arrangements. Single-end fed. In a single-end fed configuration, direct current is injected from one landing station only. The return path is through a seabed electrode into the ocean and back to shore ground. Single-end feed is used for short systems or during maintenance when one end is unavailable. Because all repeaters must be powered from one side, the maximum number of repeaters, and therefore the maximum reach, is limited by the station's voltage ceiling and cable resistance. Double-end fed. In a double-end fed configuration, both landing stations provide current into the central copper conductor with their grounds tied to seawater electrodes. The repeater chain floats at a high potential between the two ends, so voltage stress is shared and total reach is longer. Power feed equipment runs in constant current mode and monitors insulation resistance, leakage, and repeater current draw. Branching units contain shunt regulators and fuses so that power can bypass a failed spur while keeping the trunk alive. Application scope. Transoceanic trunk. A transoceanic trunk spans thousands of kilometers between continents. It uses repeatered wet plant, G654.E fiber, double-end feed power, and either C-band only or C plus L-band spectrum. The route is mostly lightweight construction in deep water with armored segments and burial near the shelves. Capacity is scaled through many fiber pairs in a space division multiplex design and through periodic terminal upgrades on shore. Regional. A regional system connects countries within a sea basin or links a mainland to nearby islands with spans from a few hundred to 1,000 kilometers. It can be repeatered or unrepeatered depending on distance and traffic goals. G652.D fiber is common because of tighter bend tolerance in branching units and shore ends. Armor classes transition frequently due to variable fishing intensity and complex coastal bathymetry. Festoon or coastal. A festoon system runs along a coastline with many landings. Spans are short and often unrepeatered. Branching units are frequent, burial is extensive where soils allow, and armored or rock-armored construction protects sections that cross harbors, river mouths, or rocky headlands. Because spans are short, terminals can operate at lower launch power with high wavelength counts while keeping signal-to-noise ratio within margin. There's a great video on the screen now. Don't miss it.